Hey, good afternoon, everyone. So it sounds like labs started out smoothly last week. Was there any issues? Okay, sounds good. I'm going to start out by quickly going through quiz 1 from last week, and don't forget to take quiz 2 that's posted on Dropbox for this week. You have till Sunday to take it. I think there was 7 questions. The first question was, what is the size of a peripheral's I/O space whose address begins at 1100 in hex and ends at address 0CEF in hex? And so that one, you just have to subtract in hex, get the difference, which is going to be, in hex, the difference is 1 BEF, and that's base 16. The base 10 representation is 7,151. And then you have to add 1 to that because that is an inclusive range of addresses. So the answer there is 7,152. Any questions about that? Okay. Suppose variable b contains the value, the hex value 1234. To what value will it change after executing the code? B equals b and then bitwise OR, 1 shifted by 5 bits to the left. Okay, so basically this code turns on bit 5 because you take the value 1, which is a value with bit 0 set, and you shift it 5 bits to the left, which turns on bit 5. So, basically you get a temporary value there where all the bits are 0 except for bit 5, and then you do a bitwise OR, which turns on bit 5 in the variable b if it was already if it was off, if it was a 0, and if it was a 1, there's no change. So the question is, we've got a hex value here in the variable b, and we're turning on bit 5, so where does bit 5, where does that go? So bit 5 would be in the second hex digit. Everyone see that? Because you basically shift 4 bits, so you pass up this least significant hex digit gets, you pass that as you shift 5 bit positions to the left. And that ends up being a 1 in bit position 1 in the second hex digit. When you say, where'd you get 1? Well, it's 5 minus 4. You subtract 4, which is the bits that correspond to the rightmost hexadecimal digit. Does that make sense? Okay, and so in this case, if you look at that hex digit as a 3 there, bit 1's already set. So this code actually doesn't change b at all because you're doing a bitwise OR, you're ORing together 2 1s, or you're ORing 2 1s in bit position 5 that already, both were 1, right? So it doesn't change the value. Okay, next question is, suppose variable b contains the value 1234 in hex. To what value will it change after executing the code? And this one's a little bit more complicated. So this one is a bitwise and we're taking 1, shifting it 5 bits to the left as we were before, but this time we're subtracting 1. So when you do that, if you take 1, shift it 5 bits, and then subtract the value of 1, it basically goes from being 1 followed by 4 zeros, right? So this intermediate value is 1 followed by 4 zeros. And when you subtract 1, you get just 4 1s, right? So you basically go from the decimal value of 32, which is 2 to the 5th power. You subtract 1, it makes it 31, which in decimal is just not a big deal. But if you look at it in binary, you go from 1 followed by 4 zeros to just 4 1s, right? So that gives you, that basically the purpose there is to set up a bit mask, where you have a sequence of 1s, okay? And then you shift that to the left by 1 bit, so you end up with 5 1s and a 0, right? You guys with me? And then you AND that with B, so it creates a bit mask where it basically allows bits 5 down to 1 through the bit mask. Okay, so that's just what I explained. So 1 shifted by 5 bits minus 1 gives the binary value 5 1s. Then if you shift that to the left by 1, it adds a 0 there. on the right-hand side. And then use this as a bit mask. Now the question is, how does that affect the hex value that I have? One way to solve this would be to convert this hex value to binary and just do the whole thing in binary. I'm taking a little bit of a shortcut here. So the idea is that if you look at the bit mask, this is bits 5 down to 1, right? 0, 1, 2, 3, 4, 5, and down to 1, right? So if you look at these, the value 1, 2, 3, 4, that range of bits is really only covers the last two, or the least significant two hex digits, right? Because this is 7 down to 0, these two digits, right? You guys with me? It's 8 bits. So this mask only affects, or only matches up with, the rightmost two hex digits. So what's going to end up happening is that 1 and 2, the first two hex digits are going to get masked off. They're going to just become 0, right? And then the 3, 4 may or may not be changed depending on if the 3, 4 value in binary lines up under the bit mask. So 3, 4, so 0, 0, 1, 1, 1, 0, 0, sorry, 0, 1, 0, 0, right? So that's 3, 4, right? I do that right? And the value we're masking there is a 1 on the right. So going from right to left, it's a 0 on the right. So if you go from right to left, you 0, 1, 1, 1, 1, 1, right? 1, 2, 3, 4, 5. Make sense? I do that right? Okay, so what ends up happening is that all the 1 bits, all of the bits that are set to 1 in the original 3, 4 in hex line up with the bit mask, and so basically it ends up not changing. The bit mask doesn't change anything. The 3, 4 survive. The hex digits 3, 4 survive the bit mask, right? You guys with me? Okay. Okay, so the answer is just 0, 0, 3, 4. I think in the quiz it was just, I think I eliminated the leading zeros in the quiz. I just said 3, 4 as the answer. Okay. Support, well, I was supposed to say suppose, that was a typo. But I assume you guys all knew what I meant because no one asked about that. You want to set bit 3 and variable b to 0. Which line of code will accomplish this? There's 4 options here. This first one turns off bit 0. Why does it do that? Because b and complement 1, tilde 1, bitwise complement 1. So this will basically, tilde 1 is going to create all 1s in a 0 on the right side, right, in the bit position 0. So this bit mask just turns off bit 0 in B and leaves it otherwise unchanged. And then we shift that result 3 bits to the left. So, I mean, that doesn't even remotely accomplish what we're trying to do. So that's not the right answer. The second one says B equals B or 1 shifted to the left by 3. This turns on bit 3, and that's what we wanted to do. So the answer is B. This is pretty much right out of the lecture slides. This was one of the ways I recommended that you do that. The other option is B equals B or 1 shifted by 3 bits and then negated. That would turn on every bit but bit 3, so that's not the right answer. And then B equals B and 1 shifted by 3 tilde. This turns off bit 3, right? So the answer is, in this case, the answer is B. Although when you take the quiz, it might have not been B. The answers are shuffled, right? The option enumerations are shuffled. Okay, suppose there's a 32-bit value named IOStat containing the bit field 4 down to 2 that you need to read. What expression will accomplish this? Okay, so this one turns off all except bits 4 down to 0, which is what's happening in here. So 1 shifted by 5 minus 1 is just going to create 5 1 bits, but then you're going to do a negation, a complement of that. So this will turn off all but bits 4 down to 0. Make sense? Like if I didn't have the tilde there, it would have just isolated the 5 rightmost bits, right? But because I put that tilde there, I did the opposite and I isolated all but the 5 low order bits. Make sense? And then shift that value to the right by 2. Right? Well, that doesn't do what we're trying to do. Turns off all except bits 4 down to 0, shifts the result to the right by 2 bits. So basically the result is that the original bits, when I say original I mean IO stat, whatever IO stat was, it takes bits 31 down to 5 because it had knocked out 4 down to 0, and it adjusts them to become the new positions 29 down to 3, right? So that does not work. Now it would have been fine had I not put the tilde there. Okay. All right, the second option, now I don't think I showed this version in lecture, but as long as you understand what shifting does, you can kind of see how it works. So in this case, you take IO stat, so here's bit 31 down to 0, and if you shift that to the right, to the left, right? You do a left shift by 27, that's going to take bit 4, and it moves it all the way into bit 31. Make sense? Because, 4 plus 27 is 31. Right? Likewise, bit 0 is going to become bit 27. Right? Okay. Now, once I finish that, I shift the result of that to the right by 29 bits, which is going to take bit 31, which was originally bit 4, right? So it was bit 4, it became bit 31, but now it's going to subtract 29, so now it's going to be 2, right? Because 31 minus 27 is 2. Okay, so when I did the first shift to the left, I filled in everything on the right with zeros. When I did the second shift to the right, I filled in everything on the left-hand side with zeros. So basically we end up with, in the end, is just you isolate the bits, the original bits 4, 3, and 2. They get moved down to bit positions 2, 1, and 0. But also at the same time, all the other bits get zeroed out, right? Because when I shifted left, I backfilled everything to the right of that with zeros, and then when I shifted back to the right, I backfilled everything to the left of that with zeros, right? So this is another way you can isolate a bit field, right? So that works. And then one of the options was all of these, and then D was IO stat shifted, take the original value, shifted 2 bits to the right. That puts bit position 2 into bit position 0, and bit position 4 into bit position 2. And then you mask off the 3 low order bits, and then you end up with, nothing left over except bit position 4 down to 2, right? Or 0, 1, 2, 5 down to 2, rather. Right? So that works. That one's good. And then finally, shift everything by 2 to the right, which is how we started the last one off. And does not show that actually. Oh, so I did wait, did I screw that up? So we're gonna, yeah, it should do a shift right by 2, which I show down here. But that should have happened first, actually. So the idea is that I'm going to start out by shifting to the right by 2, and then I'm going to mask off the low order 3 bits, right? And that's also equivalent, because remember, we're trying to get 3 bits, 5, 4, 3, 2, right? 4 bits. Was it 5 or 4? 4 down it. Yeah, sorry, not 5. I had the starting index wrong, right? Yeah, sorry, it was 4. Thank you. Yeah, 4, 3, 2, right? 3 bits, right? So I want 3 bits, but I want starting at bit position 2. So you do the shift, which knocks off bit position 0 and 1, and then you mask to isolate what are now the 3 low order bits, which were originally 4 down to 2. You guys with me? Okay. All right. So going back and looking at this, option B was good, D was good, and E was good, but the first one was not, right? So this first option didn't work. So what ended up happening was there was a typo in this question. That tilde shouldn't have been there, right? So everyone got this one right because there was a typo in it. But if you were confused by this one, that was why. Okay. Okay. Which of the following bit sequences shows a pulse width modulation signal with duty cycle 2, period 5? Duty cycle 2 means it's high for 2 units a time and low for 5 minus 2 units a time. So this first one looks good, right? 2 high, 3 low, 2 high, 3 low, and this would repeat, right? Okay. Assume a peripheral can raise interrupt every 20 milliseconds. What's the maximum possible interrupt rate for a CPU configured with an edge triggered interrupt? Just 1 over 20 milliseconds, 1 over 0.02, which is 50 interrupts per second. Okay, that's it. Any questions? Yes?
Yeah, on question 7.
That was the last one, right? Yeah.
Is it assumed that an edge-triggered interrupt will only trigger on one of the 2 edges? Because presumably if it can raise an interrupt every 20 milliseconds, it can also lower the interrupt every 12 milliseconds. Because it cannot be raised while it's at 1. It must be lowered during that time.
Yeah, that was a little ambiguous. Yeah, I said it can raise interrupt every 20 seconds. I mean, it's implied that if it can raise it every 20 milliseconds and it's able to lower it, in the interim time between every time it raises it, or each time it raises.
Case, wouldn't the maximum be 100 times per second because it can raise and lower, assumedly, every 20 milliseconds, and then it's configured for an edge-triggered interrupt?
Yeah, you know what? That's a good point. I meant rising edge triggered, but I didn't say that. I just said edge triggered. So that is a good point. Yeah, was that an option? 100? If that was an option, then I'll mark that one as correct as well. Yeah, I don't remember if that was one of the possible answers, but yeah, that's legit. Yeah, I should have said I meant rising edge. I just didn't state that. Okay, great. Okay, so continuing on here with the lecture. So last time we talked about SPI. SPI is a synchronous, just to quickly review, and if you have any questions or if there's anything still unclear about SPI, please feel free to ask. So SPI is a synchronous master-slave style protocol. It has 4 wires that make up a channel. There's 3 wires that flow from the master to the slave, and then there's one that flows the opposite direction. So there's clock, slave select, and MOSI go one direction, and then MISO comes the other direction. It's based on exchanging 8-bit words, but it's a serial protocol. So 1 bit goes through the channel per cycle, but you could think of it as every 8 cycles, 8 bits have been transferred, and they're interpreted as a byte. Now, what does that really mean? It means that all of the SPI transactions are supposed to occur over the course of a number of clock cycles that's evenly divisible by 8, right? 2 or more exchanges comprise a read or write transaction. So that's a terminology thing that's a little confusing, I think. It took me a while before I was comfortable with that. But an exchange is basically swapping a byte, whereas a transaction is where you swap multiple bytes in order to achieve a transaction, which is a read or write request. You guys with me? Okay. There are 4 timing modes. Why? I don't know. I don't know why. This is just a weird thing about SPI. I think I can't imagine why this exists, but there's 4 timing modes where basically you've got clock polarity, which defines whether the clock idles high or low, and clock phase, which determines which edge of the clock the first bit is read when you start a new exchange or a new transaction, when you initiate an operation. You guys with me? So if CFA is 0, then it's the first clock edge is where you read the data, where both sides read, because remember they're exchanging, so both ends are reading. And they're both sending data too, but they're basically, as I explained last time, they send the bit out a half clock cycle before it's read, is the idea, right? So if you look at the timing diagram, when you read a bit, you're supposed to have that bit stabilized, meaning that it probably changed 1/2 clock cycle prior to the clock edge it's supposed to be read on. Okay, so anyway, CFA means read on the first edge. CFA equals 0 means read on the first edge. CFA equals 1 means read on the second edge. And then is the second edge rising or falling? Well, that depends on the clock polarity, right? If the clock polarity was 0, that means the clock idles at 0, which means the first edge is rising. Okay? All right. And then there are ways to have one master, which is like the CPU, and then multiple slaves. There's 2 different ways to arrange that. You could either do it as a daisy chain or a multi, or you can have multiple slave selects that go out to each master. The problem with SPI is that there's no multi-master mode, which is a big problem with SPI. You can have multiple slaves, but you can only have one master, and that's no good because that basically limits you to have one processor there. So today we're going to talk about I2C that allows anyone can take mastership of the bus. And then I talked about lab 1 last time. I talked about it in class, and then I reviewed it in the Wednesday lab, and Philip reviewed it on the Thursday lab. But basically, the idea is to use an API that we provide to read a signal trace file, and then to interpret the signal trace as a series of SPI transactions. The API is very simple. It basically just has two functions in it. Essentially, there's a function that initializes things and frees up the memory. But when you're using it, there's really just 2 functions: find next edge and give me the signal at a certain time. The next edge, when I was on Wednesday, I think the next edge is what gave was a little confusing to some of the groups. They're like, well, what are we looking where? What signal are we looking for edges on? Well, there's actually there's 2, right? Initially, you're looking for an edge on slave select to find out when the transaction starts, and then from that, then during the transaction, you're looking for the edges on the clock, right? Now that edge now in the case of slave select, it's always the falling edge you're looking for, right? But on the clock, it could be the rising or falling depending on CPOL and CFA. So in a nutshell, that's really the whole sort of challenge of the lab is to figure that part out. Okay. Okay, and that's it. That was lab 1. Okay, so the next topic is UART, which is another type of channel. I normally cover this first because it's actually the simplest protocol, but I wanted to cover SPI first so we could get you started on the lab as early as possible. UART stands for Universal Asynchronous Receiver Transmitter, and as you I'm sure gather by the name, it is an asynchronous protocol, meaning it has no clock. And that's also the most annoying thing about it. I don't know if you guys have ever used UART before, but the problem with it is that both sides of the connection have to agree on the clock rate. And so one side will generate data based on its clock, and the other side will receive data based on its clock. And if those 2 clocks don't match, then it doesn't work. But there's no way to detect that it doesn't work other than it just doesn't work. You plug your serial cable into your switch or your power distribution unit or whatever it is you're trying to talk to, your oscilloscope. A lot of things have these UART connectors on them. or your FPGA, and it just doesn't work. And usually, in my experience, it comes down to just trial and error to figure out. I mean, you could read the documentation, but who does that, right? So usually I end up trying all the different speeds till I find one that actually works, right? But that's basically the idea, is that both sides have to agree beforehand on what the speed of the channel is. There's only 3 wires. There's essentially just 1 bit that goes each way. Now, on one side of the connection, you'll have a transmit and a receive, and the transmit will then just connect to the receive on the other side, and vice versa. So from the perspective of each host, they both have transmit and receive, but when you connect them together, you have to cross those 2 wires, right? So the transmit on one is connected to the receive on the other, and vice versa. And then there's just a ground that provides a reference for the voltage on those wires. Now the UART is designed for text, like terminals. So it's relatively low speed, and it's meant to be as simple as possible. It does have a little bit of a, you do have to understand there is a very simple protocol though. There is whenever you want to send a character or a word, you have to start out with a start bit. Now the channel idles, when I say the channel, I'm talking about either of the 2 data lines. Idles at 1, at whatever your 1 voltage is, right? Your high voltage. And the start bit is 1 clock cycle of the value being at the low voltage, ground, right? That signals to the other side that you want to send something. And then you just send each bit. Now there's no clock, so it's the responsibility of the sender to ensure that each bit that's being sent is being held for 1 clock cycle, however long the clock cycle is, whatever speed it's running the channel at. Okay, and that speed is called the baud rate. Okay, and then when it finishes, there's a stop bit that is basically 1 bit time, 1 clock cycle of the channel being high. Now you might say, wait a second, start is low and stop is high. Why is that? Well, they're meant to be different, right? Start is low because the channel idles high, and stop is high because if you wanted to send another word immediately after this one, then it would basically separate each transaction by the stop, the stop and then the subsequent start, right? So it separates the two values being sent. Make sense? Okay, right. Okay, I just covered that. Okay, now there are some other options that you can use. However, just like with the speed of the channel, both sides have to agree to these options. So one of them is a parity bit, which is an error detection bit that's added to the end of each byte. UART is 1 byte, so you send 8 bits in every transaction, but you're not really, in each transaction, right? So the parity bit comes after the byte, but before the stop bit. And it represents a slot, a clock cycle, which would be essentially the 9th cycle, right? Because the first cycle is going to be start, then you've got 8 bits, right, of data, then the 9th one is going to be this parity, if you have parity enabled. If you don't have parity enabled, you don't have a slot for the parity. Okay? Now the parity is an error detection mechanism. That's added to allow the receiving side of the channel to know if there was an error. And so the idea is that you can choose between odd parity and even parity. If you have so in the case of odd parity, and this part is a little counterintuitive, I think. So some of you might have heard of parity, right? Parity is essentially determines whether you have an even or an odd number of 1 bits that are sent, right? Make sense? Now you would think, if I just told you that there's a bit that's odd parity, you might assume that that means that if there's an odd number of 1 bits in the byte that was sent, you would set that bit high, right? That's what you might think, but that's wrong. It turns out that it's actually the opposite. If you have an odd parity bit, it means that the total number of 1 bits comprising the data in the parity bit inclusive, right, the whole thing together, has an odd number of 1 bits. Right? So the effect of that is that if the data byte had an even number, then the parity would be high, because then that would make it odd. You guys make sense? Right? So basically, what that means is that if you're using odd parity, the odd parity is true if there's an even number of 1 bits in the byte, because by adding that extra 1 bit, you now make the total number of 1 bits odd. Make sense? And then even is the same way, except with even. Okay, I'll show you an example of that in just a minute. There's baud rate. I mentioned that already. That's basically the signaling rate, the clock speed of the channel. The baud rate is not the same as the throughput, though, because the throughput, if you calculate the throughput in terms of how many actual data bits you send across the channel, then the throughput is going to be the baud rate, but you have to multiply that by the ratio of data bits to total bits, right? So if there's 8 data bits and you have a start, stop, and parity, you actually have 11 total bits. So the throughput would be 8 over 11 multiplied by the baud rate. Yes?
So why is it still a byte if there's 11 or more bits in it? That's what I don't get.
So the byte is the payload. So the start bit and the stop bit and the optional parity bit. And actually, there could be more. You could configure the channel with more than one. I know you can. I think you can set up more than one stop bit. I don't know if you can set it up with more than one start bit. But there's some options that change the overhead in terms of the number of bits that are not data bits, right? So there's 8 data bits, but there can be 2 or more miscellaneous bits that are used for framing.
So how does it know what the payload looks like? Like, it must know to look for 10, 11 bits, right?
Yes, yeah. So both sides have to agree on number of start bits, number of stop bits, number of parity bits, and they have to agree on the clock rate. And so the idea is that if I'm sitting on the receive side of a UART channel, a lot of times, whenever the channel's idle, my receive line coming in is just going to be high, right? The second that goes low and there's a falling edge, I know, well, there's something coming in. So the first thing I have to do is don't start reading the channel yet, because right after that falling edge, I have to give it 1 bit time or 1 clock cycle that I have to basically ignore, because that's the start, right? The start bit. And then the next bit after that is going to be my first data bit, right? And so I want to start reading at that point, right? And then I want to read that bit and then 7 more bits, right? Now, the problem is how fast do I read? What is the interval that I gobble a bit off the channel? Well, that depends on the baud rate, right? Now, if what I'm assuming is that my understanding of the baud rate matches the sender's understanding of the baud rate, right? And so if they both match, then if I read at, say, 9,600 times per second, if it's a 9,600 baud, then I should get all the bits, right? But I'm just taking this on faith because there's no clock. There's no clock in the channel, so I just have to read at the rate I want to read at and just hope that I'm synchronized with the channel. Yes?
Yeah, because it's an asynchronous protocol, and because there's no clock rate negotiation or anything in there, you can easily end up in a situation where you connect to some embedded device and you get back total gibberish, and you just have to try a bunch of different common baud rates until one of them starts actually spitting out ASCII characters on your terminal the way you expect. Like, you have to guess if you don't know the parameters in it.
Or you can look it up, but I never do
Right.
that. So like if you have an Arduino chip, for instance, if you read in there, you might be able to find out. But then again, even then you might not know, because the Arduino chip actually supports multiple baud rates, and the software, you don't actually necessarily know what the software set it up to run at. So sometimes you literally just have to guess. But it can be challenging because the baud rate's only one of the things you have to guess. You have to also guess the number of parity bits, the number of start bits, and number of stop bits. Luckily, in this day and age, and in my experience, usually it's 8 data bits. Actually, there could be a different number of data bits too. I didn't mention that, I should have.
Yeah.
Normally there's 8 data bits, but technically you could have more or less. But 8 data bits is the standard. No parity, and 1 stop bit. So they call that 8 and 1. 8 data bits, no parity, 1 stop bit. And that I think I just confirmed for myself that the number of start bits is always 1. The number of stop bits can be more than 1, although usually it's only 1. And number of data bits is 8, and there's often no parity. But those are things that, again, technically you could change those settings, but both sides of the connection would have to be set up properly for communication to take place. So normally if you get a new peripheral and you want to talk to it over JTAG, UART, you're supposed to look at the data sheet and find out how to set up your terminal properly to talk to it. Or you can just guess like Philip and I do. Because normally, and you might say, what happens if you set it up wrong? Well, if you set it up wrong, you either get nothing at all, or you'll get gibberish, you'll get garbage. And so it's pretty easy to know if you got it wrong. Okay, so here's an example. Now this is a little misleading because this waveform shows both the transmit and the receive side are lined up, almost like SPI, right? But that doesn't have to be the case. I don't have to always be sending something at the same time I'm receiving something. And you might say, well, then why does it look like that? Well, because the code I wrote to generate this plot was an adaptation of my SPI code. So, but also I wanted to show both wires. I didn't want to just have one. But you don't have to, like I said, you can send bytes without having receiving any, without receiving them, right? Or you don't even have to have both wires connected. If you just connect one of the 2 wires, you can have one-way communication between 2 endpoints. That's fine too. Nothing wrong with that. But if you want to have an interactive session where, you have a terminal and you have a prompt and you could type in commands, and you need to have both wires connected. But they don't have to be. With SPI, all the wires have to be connected. Okay, well here's an example. 7 data bits, least significant bit sent first, no parity, 2 stop bits. So how do I read this? Well, the first things start out is I have this don't care shaded region. So that is meant to imply to you that there's no transaction going on in there, right? The transaction starts when the signal is driven low, and there's always starts with this falling edge, right? So because of the start bit, right? Start bit is 0, right? The start bit value is 0, right? The start bit is actually referring to the time slot where the start bit is sent, but the start bit value is 0. So you're always going to start with a 0, and then you have data. So how do I read the data? Well, you just pretty much just follow the waveform. So I'm sending a 0, 0, 0, 0, 0, 0, 1. That's 7, if I counted right. So 6 zeros and a 1. And then I would have a parity next, but there's no parity here. No parity. So, but I do have 2 stop bits, and stop bits are always value 1. So 2 stop bits there. Right. So you might say, wait a second, I thought you said that most of these channels are 8 bits. Yeah, most are, but I'll ask you, I might say 7 bits or 9 bits or whatever, just to force you to count, you know. And also, like I said, technically you can do this with UART. You can have 7 bits as long as both sides agree. Okay. Likewise, on the receive end, I have start and then 1, 1, 1, 1, 1, 0, 0. Now it's least significant bit first, so in order to translate this to like hex, I have to reverse the order, right? So in hex, it would be, you know, it would be like the low order hex digit would be 1, 1, 1, 1, so F, right? And then the high order hex digit would be 0, 0, 1. So this would be 1F being received, right? So you read backwards. Okay? Make sense? So that's a pretty easy protocol compared to the other ones that we'll cover. So this one just shows, I show the start bit there, and this data being sent is 6 zeros, 1, 2, 3, 4, 5, 6 zeros and a 1, but you have to, like I said, you have to reverse it because I said that it's least significant bit first. So that would be, in hex, it would be 4, 0, because 1, 0, 1, 0, 0. Oh man, that's missing a 0 in there. That should be 1, 2, 3, 4, 5. There should be 6 zeros, sorry. Yeah, there we go. That looks better. Okay. The hex is right. It is 4, 0, but it's 1 and then 6 zeros, right? It's 4, 0 in hex. Okay. Okay, and then, you know, stop bits are at the end. Okay, so here's another kind of question I'll ask you is what bytes are exchanged? Now, the thing about parity is that normally parity is used to detect errors. Right, so if the parity bit is inconsistent with the bits that are sent, like if it's an odd parity, you count the 1 bits and there's an even number of them, then there's a problem somewhere, right? However, if you know which bit is an error, then it becomes what's called an erasure, an error correction coding. An erasure is where you know that there's an error, and you know the position of the error, and you can use the parity to actually fix the error. You can correct it. Now, do you normally know where the error is if you get an error in a UART channel? No, I don't think so, unless there's a way that you have a receiver that can measure noise margins or something, like measure, detect that there was an error. I've never seen hardware that can do that, but here's, in this example, just for the purpose of this question, let's assume that we know that we have an error here. And so the question is, what bytes are exchanged? Well, the first one's pretty easy. You just look at the waveform. The second one's harder because we have a missing bit, but because there's a parity bit in here, we can figure out what that missing bit is, right? So there's 9 bits, 9 total data bits. So, and it's even parity. So let's count the number of 1 bits, starting from bit 2, which is the first data bit. You don't include the start when you do a parity calculation, and you don't include the stop either, right? Just the data in parity. So, so starting with bit position, the second bit, there's 1, 2, 3 1 bits, and then 4, 5. So there's 5 1 bits, okay? And then the parity is 0. So there's 5 1 bits. So that's odd, right? But that's not allowed because it's even parity, which means that that missing one must have been a 1 to make it an even number, right? And so this is least significant bit first. So, so the first bit, now again here, don't include the stop, so I'm going to, and don't include the parity. Right? So if I just want to extract the byte or the 9 bits that were sent, I don't include the stop and I don't include the parity. I'm going to start here, right? Which is this is the most significant data bit, right? And there's 9, so in hex that would be a 0 in hex. And the next hex digit would be 1110, right, which is E, right? So 0E, and then 1110, another E, right? So EE, I get that right? Yep, EE, 0EE, right? You might say, wait a second, whoa, why is there 3 hex digits if there's only 9 bits? Wouldn't 3 hex digits give you 3 times 4, 12 bits? Yeah, but if you have a number of bits that's not divisible by 4, then you just 0 pad, right? So that leading 0 there is intended to represent just that 0 binary value. I just assume the other bits are, and the hex digit are 0. Make sense? Okay. All right. Any questions about that? Okay. Okay, assume a UART channel operates at baud rate 9600 BPS, bits per second, and has 7 data bits, 1 parity bit, and 1 stop bit. What is its throughput? Okay, so this would be 9600 bits per second. That's the raw speed of bits flowing through the channel, but I'm only getting 7 data bits for every 7 plus 1 parity bit, 1 start, 1 stop. So for every 10 bits, right, there's 3 overhead bits, right? Parity, start, and stop, right? You guys with me? So 7 out of 10. Now, by the way, you don't have to continuously send data on a UART channel either, right? In fact, if you're using it as a console, you probably won't do that very often, right? You're probably just sending 1 keystroke at a time, right? But if you wanted to saturate the channel and try to push as much data through it, then you would only be sending 7 bits for every 10, so you'd only be getting 70% of the 9600 baud, right? So yeah, 7 data bits for every start bit, 7 data bits and parity bit and stop bit. Right, so there's 7 bits for every 10 bits. That means there's 70% of the bits that are used for data, or sorry, 70% of the total bits are used for data. The throughput is 70% times 9600, which is 6,720 bits per second. Okay, here's another example. Which bit is missing? Odd parity, 2 stop bits. Okay, 2 stop bits. Okay, and so I'm just going to start at the right and work my way left so I don't get confused by these stop bits. So there's a 0. So there's just counting 1 bits now. We've got 1, 2, 3. 3 1 bits. That's between the stop and the start, right? 1, 2, 3, right?
It's missing a 1.
Right. So yeah. So it must be. Let's see. 1, 2, 3. Well, no, that's odd parity, so it should be a 0 actually, right? Because 3, the number of bits is already odd, so I don't have to add another 1 bit there.
Isn't it logic high if it already has an odd parity though?
For all the bits. See, that was the part I said. It's 0. So the parity is 0, and the total number of 1 bits currently in here is 3, right? Right, so 3 is already odd, right? So if there was a 0 here, right, then that means there's an odd number of 1 bits,
Okay.
right? So it should be a 0, yeah, 0. Yeah, try, I always find that confusing too. It's not, see, the parity bit is not intended to be a signal in and of itself telling you whether it's even or odd. It's meant to pad out the bits to make the total number of 1 bits even or odd, right? It's meant to correct the number of 1 bits, right? But if you think of a signal, if you think of it as a separate flag, then you could just reverse the logic and say that odd parity is 1 when there's an even number, right? But that's even more, to me, that's even more confusing. Okay, so here's another one. Are there errors in the transaction below? Well, you got to check both sides now. 5 data bits, 1 stop bit. So I'm going to start from the right again here. So there's just 1 1 bit here. odd parity, it's fine. Now, keep in mind that there could still be errors if there's 2 bit flips. There could be 2 errors, in which case parity wouldn't be enough. There'd be too many errors for parity to detect, right? Parity can only detect up to 1 error. So I should have said, are there errors in the transaction that are detectable by parity? Okay, here we've got 1, 2, 3, 4, right? 4 1 bits. So there is an error, but it's on the receive side. Yeah, receive parity is incorrect. Okay, and that's all I've got for UART. Make sense? Okay, so UART is, in my opinion, it's even simpler than SPI, but it generally doesn't run as fast as SPI. SPI is a megahertz range, whereas the fastest you can really run UART is 57,000 baud, and oftentimes even less. What value is, okay, so let's go back to SPI. I talked about this briefly last lecture, is this idea of having more than one slave side or peripheral on an SPI bus, channel, whatever you want to call it. I mentioned that there's a couple ways you can do that. One way is to have a separate slave select for each one of the peripherals, right? Then you can just activate whichever one you want, right? So obviously that requires extra pins for this guy, right? But there's a bigger problem here. The bigger problem is that the meso lines coming out of these guys are all connected, in this case, the way this is shown, because I'm assuming that I can have multiple slave selects on the master, but only one meso and one mosi, right? I'm making that assumption. If that's the case, then these guys are all going to be connected to one meso. They're going to be shorted to one line, right? Which means that if you look at the meso as kind of the thing that they're controlling, then you've got multiple masters of the meso line, right? Multiple devices that could take charge of the meso line, right? They might say, why is that a problem? Well, it isn't necessarily a problem, but you have to be careful because there's some things you have to consider here. The assumption is that if you're communicating with one of the peripherals, the other one shouldn't be sending anything on that meso, right? But that requires that it's able to disengage itself, like to electrically disconnect itself. And we call that high impedance, basically, meaning that what that means is that if you look at what signal the unaddressed peripheral is sending on meso when it's not being addressed or not being engaged, it's going to be Z, which is kind of like a third value. You know, we've got 1 and 0, right? These are binary. But Z is like a third value now we can send. So I can send a 1 or a 0 or a Z, meaning Z means I'm not sending anything. I'm going to disengage from the bus. Okay? Now you might say, why is that important? Why do we care? Why do we have to be disengaged? Well, to understand that, we got to go back and talk about transistors for a second here. So, I don't know if you guys haven't, some of you guys have taken electronics, right? Electrical 371. Some of you have, some of you haven't. So, I'm sure you know that like digital chips are built with transistors, which transistors form the logic gates, and you learn about logic gates in 211. So there's two types of transistors. There's an Nmos and a Pmos, and both of them act like, or at least when you use them in digital logic. This isn't always the case. You know, analog logic is different, but in digital logic, you treat these transistors as switches. They're either on or off. And so an NMOS both transistors have 3 terminals. They have a gate, a source, and a drain. The gate controls whether the source and drain are connected electrically or not. Now, when I say connected electrically, technically they're always connected electrically, but if you turn off the transistor, it raises the impedance between the source and drain to like mega ohm scale, And when the gate is on, when the transistor's on, it reduces the impedance between the source and drain to something like less than an ohm, right? So it's not really turning off and on, but it's really kind of like making the resistance super high or super low, essentially, right? Now, the difference between NMOS and PMOS is which value of the gate turns it on or off. So in the case of an NMOS, if the gate is 1, meaning logic level 1, which means, whatever your VDD, your power supply is, that turns the transistor on, and if your gate is 0, it turns it off, right? And again, on means connect, drain, and source. Off means disconnect, drain, and source. On means connect, drain, and source, right? PMOS is just the opposite. And the way you know that is if you look at the symbol for a PMOS, you see there's a little bubble there on the gate. That's a little, hopefully you remember from 211, that's an inversion bubble. And so that just means that the gate is active low, logic, negative logic, active low. 0 means on, right? Make sense? Okay, so now that being said, you obviously build gates out of these things, but you also build drivers to set an external pin to 1 or 0. And so I'm talking about like in SPI, the clock, MOSI, MISO, slave select, they are connected to a driver. And if you build the drivers using what's called push-pull logic, then this is one way to build them. This is kind of the obvious way to build them, is essentially you connect the connections, like for example, MISO. Like now, say I have 2 chips, they're both driving the MISO. How do they actually drive it? How do they pull that wire to 1 or 0? Well, they connect it to an inverter, basically. And so an inverter has an NMOS and a PMOS. And so the idea is that if you want to pull that wire up to VDD, you want to set it to 1, you turn on the PMOS here, and you connect this guy to 1, to the power supply. And at the same time, you disconnect them from ground. So you turn on the PMOS and you turn off the NMOS, right? So you basically turn this guy off, turn this guy on, and you pull it up. You short that wire to VDD. And if you want to pull it down to 0, you want to send a 0 out on MISO, then you turn off the PMOS, you turn on the NMOS, and you pull that wire down. When I say pull it means you take that wire and you make the transistors electrically short it to 0. Pull it down, right? Drive it to 0, right? The problem here is that if I have 2 slaves, they're both connected to MISO, and let's say one of them pulls up, turns on the PMOS, and the other, now keep in mind, these are endpoints, so these are chips. So these are chips inside these boxes, and this is the wire that connects them across the circuit board, right? Or the cable. But usually, it could be a cable or a circuit board trace, either way, right? Or it could be an on-chip trace. So if I pull up one entity, one of the slaves says, I'm going to pull up, I want to drive the wire, the MISO wire, I want it to be 1. And the other one says, I want to pull it to 0, I want it to be 0. Now we have a conflict. And this is pretty bad because I mentioned that when you turn a transistor on, its effective resistance between the source and the drain is about 1 ohm, usually I think less than an ohm, depending on the size. Depending on the size of the transistor. You put a big transistor, the resistance is less when it's on, right? But usually you use pretty big transistors when you're driving wires, because there's a lot of capacitance, right? So let's just say 1 ohm, right? So let's say I turn this guy on, and I turn this guy on. So now I have 1 ohm through this guy, and then across the wire, and then another ohm through this guy down to ground. So now I have 2 ohms effective resistance between power and ground through both chips. So I'm sourcing current through this chip, and it's going to start shooting current out, which is then going to come down, and the effective impedance there is 2 ohms. So like now, if I'm over 5 volts, if it's a 5-volt signal, I've got 2.5 amps flowing between these two chips, which, now, okay, so if it's an Arduino that's powered by USB, USB is limited to 500 milliamps, right? So it'll peak out at whatever your power supply is, right? If you can't source 2.5 amps, then you're not going to get 2.5 amps. But whatever the case may be, if you turn them both on, you're gonna saturate your current. If you can't supply 2.5 amps, then it's going to cause the voltage across this thing to drop. And even, actually, I shouldn't say that. Even if you can supply 2.5 amps, the voltage here is going to be 1/2, essentially. It's going to be right in the middle. So if it's a 5-volt wire, it's a 5-volt supply, you're going to be about 2.5 volts, which is in the forbidden zone. We don't know how to interpret that, if that's a 1 or a 0, right? If it drops the current, if you're current limited, then the voltage will drop, so the power supply voltage will effectively drop, so you'll be lower here. But in any case, you'll have some undefined value, and you may end up burning your chips out, right? You don't want to do that. So basically what it means is if you have a push-pull style system, which is pretty common for like SPI or UART, you can't double drive a wire this way. So then you might say, well, then how do you have more than one slave connected to MISO? Well, you have to use some kind of a tri-state buffer then, which allows you to, like I was saying earlier, disengage, right? So a tri-state buffer is like usually 2 transistors in parallel that can turn the whole thing off or turn the whole thing on, right? But you have to be careful, though, that there's no misunderstandings when you run your system. You got to make sure that that you don't have more than one connected, non-tri-stated bus on there. But if you have tri-state bus, then you effectively get a third logic level, which is don't care or Z. So you could put a 0 or 1 or 0, 1 or Z. Everyone with me? Okay. However, there is another simpler, cheaper approach to this, and that's called the open drain type connection, type interface. So instead of using a push-pull, which is where you use a PMOS and an NMOS to pull up, push, pull, pull to 1, pull to 0. I don't know what the push is, but push-pull is like, using the style that I showed before. Another option is an open drain. And in this case, we get rid of the PMOS, right? So what that does is it only allows each chip to put a 0, not a 1. 1 is for the PMOS. PMOS is how you put a 1 out, right? But instead of the PMOS, we'll take the wire that connects the two chips and we'll install a resistor up to the power supply. And we'll put a resistance of about 10 kilo ohms on there. You gotta get that right. I've seen these like anywhere from 4.7K to 10K, something like that, right? So basically what happens is that if you turn both sides off, so let's say either these guys don't want to talk, they don't want to talk on the bus, or they just want to send a 0 on the bus, then they both turn off their NMOS. And the bus will appear to be a 1 because you'll have about a mega ohm here down to ground because the transistor's off, but you only have 10 kilo ohms up to the power supply. So if you have a 5-volt power supply, this will create a voltage divider and it will cause you to lose about 100 millivolts. So the downside is you're not going to get your full 5 volts. The highest voltage you'll see here, in this case, is 4.9 volts because you're going to have a voltage drop across this pull-up resistor, right? But that's close enough. That's not in the forbidden zone. That's still high enough to be registered as a logic 1. Now the assumption here, by the way, and I don't show it, the assumption is that we're also reading this as well. I'm only showing the drivers, right? But someone is reading this signal as well. And if they read it at 4.9 volts, then yeah, it's a 1. okay? This is just a voltage divider where you're saying the effective, now, oh, by the way, one of the problems with this though, just so you know, is that these guys are mega ohm, so you got 2 mega ohm resistors in parallel, so the effective resistance from the wire down to ground is only half of that, it's 500 kilo ohms, right? And then the resistance up to VDD is 10, so the voltage divider is 500 kilo ohms divided by 510 kilo ohms, 500 over 510, which is the total, is 4.9 volts. But the problem is if I keep putting devices on this bus, then that's going to keep dividing, it's going to keep putting parallel resistors down to ground with every new device. So one of the problems is that the more devices I put on the bus, the lower this high voltage is going to be, right? Unless I correspondingly adjust this pull-up resistor, right, as well, right? But there is a downside to this, and that's one of the downsides. You guys with me? Okay, now let's say, oh, and by the way, the leakage current through there, I mentioned there's a voltage drop. That also means there's some leakage current, but it's only about 10 microamps, right? So in other words, even if you have devices on this open drain. By the way, the reason it's called open drain is that the transistors have a source and drain, right? In the Nmos, the drain is the top terminal. On the Nmos, it's the bottom. The drain's the top. And so if you notice that we're using Nmos here, okay, the drain's the top terminal, so this drain is open. Why is it open? It's not really open, it's connected to a resistor. Well, it's open because it's open to the world, connects to the pin that goes outside the chip, right? I guess that's why they call it open. That's what they mean, open drain, right? But anyway, we're going to have some leakage current, which you wouldn't have with a push-pull. I mean, you'd have it with a push-pull, but much less. You're going to have some leakage current, about 10 microamps that are always going to be flowing, even if everyone's just not even talking on the bus. All these guys have the Nmos's off. Okay, now let's say I want to send a signal out. One of my chips wants to send a 1. I want to send a 0 because, like I said, 1 is normally what would be on there if no one's talking. So if I turn on if I have the Nmos here and I turn it on, that's going to bring the resistance here from about a mega ohm down to an ohm, right, or so, right? So it's going to connect. It's going to try to pull down, right? It's going to pull down the output to 0. So I end up there with a voltage divider here that's 1 ohm over about 10,001 ohms. So that will effectively pull that voltage down to 0. But then you might say, wait a second, hold on. Now you basically have a short circuit here between ground and VDD, which you do, except it's through this pull-up resistor. So you're going to end up with about half a milliamp flowing down through here, which isn't too bad. That's manageable. It's more than the microamp we get in leakage, but it's a lot more than we get with a push-pull style driver, but it's manageable, right? And so that allows us to put a 1 in here, which will then put a 0 out as the output on this guy. Make sense? Now what happens though if there's a conflict and both sides, they want to talk at the same time, so they both want to pull the wire down to 0. So they're going to both turn on their Nmos transistors, and what is that going to do? Is that going to cause a catastrophe like it would with the other style, push-pull? Well, no. In fact, it really doesn't change much at all. The bus will still be 0. We'll have a little bit less effective resistance, and we'll double the amount of leakage current coming down through that pull-up resistor. So we'll have about 0.5 milliamp going this way and 0.5 milliamp going that way, but manageable. We can deal with that. Okay, so that's basically the premise of these open drain style connections. And so we're going to look at this I2C, or sometimes I2C, or sometimes you actually say I2C. It stands for integrated circuit. Inter meaning it's designed for chip-to-chip communication. And it uses an open drain style, right? And it does that so it can be a multi-master, so that anyone could take mastership of the channel. Anyone that wants to be master can be master. Make sense? Okay, so it's a little bit simpler in the sense compared to SPI because it has only 2 wires. It has SDA and SCL. That stands for serial data and serial clock. Now that sometimes data sheets use different. Sometimes they use different names for those, but essentially there's a data and a clock. In this class, I call them SDA and SCL, but you may see different names used there. But like I said, the protocol, the timing will still be the same if it's I2C. So the idea is that you're going to have different devices you can hang on. Each device will connect to both wires, and then you'll have a pull-up resistor somewhere to pull those wires up to VDD. Make sense? Okay, so a couple questions here. If 2 devices are attached, what's the logic value? And I've already explained this, but I explained it in sort of a roundabout way. What's the logic value if if one device sends a 1 and another one sends a 0? So we have a conflict. I'm trying to send a 1, someone else trying to send a 0. Well, like I said, devices don't actively have to send a 1. If they do nothing, they're effectively sending a 1, right? Because all they can do is pull the bus down, right? But if one device thinks it's sending a 1 by not doing anything, its intent is to send a 1, and another device is intent to send a 0, then what happens? Well, that would basically give you this situation, and you'd have a 0. So basically, if anyone sends a 0, the whole thing's a 0, right? If no one sends anything, no one sends a 0, and then the bus is going to be a 1, right? Logic high, right? As the idea. Okay, so no catastrophes if we have a conflict. Now, of course, the problem is that you have to have a way to detect there's a conflict. So the idea is that when I'm sending a bit, I also have to listen on the bus, right? To try to detect if someone else is sending, right? How does that work? I just don't know actually how that works. There's some kind of circuit that can detect a conflict. I've never designed one, but let's just assume for I2C that there is a way to detect a conflict, right? And if there is a conflict, no biggie, no big deal. Okay? If there's a conflict with push-pull and you don't have the tri-states, turned on, or if you have 2 connections that are both tri-state on, you're both trying to send a 1 or 0, 1 and a 0, then you can have a short circuit. Okay. Okay, I'm just about out of time. So I'll continue this on next Monday, and we'll see you in class or we'll see you in lab rather this week. Don't forget to take quiz 2, and hopefully you'll be able to finish up lab 1 this week. Thank you.